Hello everybody. Today in this session we continue the basics of transformer where we left off in the last session. In the last session we had been discussing about the transformer and its phasor diagram and how it is represented as phasors in the spatial coordinates. We also represented the symbolic form of the transformer, and today we will continue the discussion from that point onwards. So, we have this transformer with a primary, a core and the secondary. One should not forget to put the dot polarities. This is to indicate that this part of the winding is in phase with this part of the winding. And there is one more information that we have to provide, that is N1 is to N2, that is the N1 number of turns or N2 number of turns. Alternatively, one may also provide the ratio, that is 1 is to N, where N is equal to N2 by N1. This is also a frequent representation of the transformer. Instead of the actual number of turns, they provide the turns ratio. N is called the turns ratio. This is called the turns ratio. Secondary turns, number of turns to the primary number of turns. And of course, we have the primary voltage E1 with the primary current I1, secondary current I2, secondary voltage E2 with some load connected at the secondary, some Z2, and there is a source here which is connected across the primary, which is the generator. It's an AC generator and we call that EG. So, we saw that the phasor diagram in the spatial coordinates, that is the alpha beta coordinates, the beta alpha, we have EG and E1 are in phase because they are one and the same voltage. Now, the dot point of E1 and the dot point of E2 will also be in phase, and therefore, let us say we have E2, and then I2 is going to lag E2 by lag or lead E2 depending upon the impedance. If it is RC or it is a lead network, then I2 will lead E2. If it is a lag kind of a network, that is inductive kind of an impedance, then I2 will lag E2. Let us say it is a lagging impedance, then you will have I2 just like that. Then I1 and I2 will be in phase, only the difference is by the turns ratio, and this is going to be I1. So, E2 is equal to N E1, I1 is equal to I2 by N. So, this is the phasor diagram. Then we also noted that inside the core there is a flux linking phi m, and from the Faraday's law we see that the induced EMF is equal to N d phi by dt, which is equal to N j phi m. Now, induced EMF E is in this direction, this is E1 direction. that is, if you are taking the induced EMF across the primary E1, N1, N1, phi m. So, either E1 or E2 one could take, and we know that they are in phase and they are along the alpha axis. Now, phi m lags E1 by 90 degrees because of the J operator. What it basically means that if I have phi m, now the vector of phi m direction is rotated by J, which is rotated anti-clockwise plus J, rotated anti-clockwise by 90 degrees to obtain the direction of the induced EMF or the induced voltage, which is E. So, this would be the phi m direction. So, this is the phasor diagram for this idealized transformer. Now, let us have a simple example to understand the various points here. So, we have a source, an AC source, so the AC source is connected to the transformer terminals. There is a core and it is a step up transformer, let us say, and this is connected to a load as shown like this. So, this is our EG, generator voltage. This is E1, the primary induced voltage across the primary of the coil. There is an E2, the secondary induced voltage across the secondary of the coil. This is Z2, the secondary impedance that is applied across the secondary terminals. We have N1 number of turns here, N2 number of turns here. There is a primary current I1 flowing into the dot. There is a secondary current I2 flowing out of the dot. And of course, there will be a flux which links the two coils and causes the energy to flow from the primary to the secondary. So, for this circuit, let us say we have 200 volts 50 hertz as the source, and let us say this is 90 turns and this is 2250 turns N2. Let us say that there is a load current of 2 amps that is flowing with a lag angle theta of cos inverse of 0.8 or power factor equals 0.8. Let us say lagging load, which means Z is inductive RL kind of a load. Now, this being the description of the circuit, let us try to see what informations that we can extract. And this is a 1:n transformer. Okay. So, let us first see what is the turns ratio. So, the turns ratio is N, which is equal to N2 by N1, which is equal to 2250 by 90, which is equal to 25. Then let us see what is the primary current. I1 equals what? The secondary current is 2 amps, because RMS. All the values generally are that are mentioned are effective values or RMS values unless otherwise specified. So, we know that N1 I1 ampere-turns should be equal to N2 I2 ampere-turns, and also from the power equation we also have earlier seen that, let me use the same notations. N1 I1 is equal to N2 I2, because we see that I1 by I2 is equal to N2 by N1, this inverse proportionality for the currents. So, therefore, we have I1 which is equal to N into I2, which is 25 into 2 amps is 50 amps. So, for a 2 amp secondary current, the primary current is 50 amp RMS, because it is a step up, because it is a step up transformer. Now, let me select this portion, copy it, go to the next page, paste. Third point, E1 equals 200 volts. So, what is E2? E2 is equal to N2 by N1 into E1, or in other words N times E1, which is equal to 25 into 200, which is 5000 volts. Note, E1 I1 is equal to 200 volts into 50 amps, which is equal to 10,000 volt amps. E2 I2, which is equal to 5000 volts into 2 amps, which is equal to 10,000 volt amps VA. So, this power balance should happen. Then, what other information can we extract from this, from this particular diagram? What is phi max that one can extract from this diagram? So, we know that E is equal to 4.44 N AC B M into F. What is this one? Flux density into AC is nothing but phi max or phi m. So, E is equal to 4.44 into N into F into phi max or phi m. One could take either the secondary side or the primary side. Taking the primary side, we have E equals, E is 200, 4.44, N is 90 turns on the primary side, 90 turns on the primary side. Frequency is given 50 hertz of the, and then phi max. This is the only unknown, and therefore phi max can be calculated, which gives about 0.01 Weber or 10 milliwebers. So, like this we get the information about the transformer using basically the fundamental law which is the Faraday's law of electromagnetism, and also one more law which is the Ampere's law. Now, let us draw the phasor diagram for this circuit. So, to draw the phasor diagram, we take the two axes in the spatial coordinates. This is the beta axis and this is the alpha axis. So, the alpha axis direction is taken as EG direction, the generator voltage direction itself. So, we have E1 which is 200 volts and we have E2 which is 5000 volts. E1 equals EG, of course, and what is given is a lagging load. I2 is lagging E2 . This is I2, this is lagging E2 by an angle which is cos inverse of 0.8. So, cos inverse of 0.8 is 36.9 degrees. So, therefore, this angle is 36.9 degrees. And what about I1? I1, now this I2 is 2 amps, I1 is 50 amps, of course I am not, this is I1 which is equal to 50 amps, and then there is phi m, this is phi m which is 10 milliwebers. Phi m is also in RMS quantity because it was calculated using RMS quantities. So, this would be the Phasor diagram for this transformer circuit. Is that clear? Okay, now let us try to understand one more important aspect in the transformer, which is the power handling capacity of the transformer. You have the small transformers, the big transformers, the huge transformers, the oil cooled transformers, so on and so forth. So, you have transformers with varying sizes, right from small signal to very high power transformers. Now, what decides the power handling capability of the transformer? So, to do that, we need to understand the mapping between the electrical and the mechanical or the physical dimensions or physical dimensions of the transformer. Physical dimensions. So, you have the electrical parameters in terms of the currents, the voltages, the power, number of turns, N1, N2, so on and so forth. And to that we need to have some kind of a relationship with the physical dimensions of the core with respect to the core sizes, the sizes of the wire gauge and things like that one. So, what is that mapping and how is that done? Let us have a look at the transformer to understand, to get a better understanding of what are the physical dimensions that we are going to talk about. Let us have a look at the transformer to understand its physical dimensions. So, you see the picture of the transformer here. The transformer consists of the terminals there. So, in a practical transformer, the terminals are brought out, and that is where the coil windings are terminated by soldering. The rectangular solid block, that is the core. In this case, the core is CRGO, that is cold rolled grain oriented silicon steel, and as the steel is conductive, electrically conductive, we would have lot of eddy currents if we had a solid block of steel, as we discussed in the last class. So, to reduce the cross sectional area for the eddy current path and thereby increase the resistivity, to increase the resistance for the eddy current path, the laminations have been put. And see that all practical transformers will have the core, the solid bulk of the core, which is laminated, and then after laminating it is all air pockets are vacuumed out and then it is varnished. So, that black color or the darkish color is due to the varnish. Now, you see at the winding at the center, which goes through a central limb. Now, this consists of both the primary and the secondary. So, the primary is wound first and then the secondary is wound on that one about the central limb. So, the core here looks slightly different. Let me give you a better idea by drawing the two dimensional view. The core will be something like this. So, we have this rectangular block, solid block, and then we have a central limb. We have a central limb. Now, the winding is done on the central limb here in this case. So, you see the winding is done on the central limb. So, let us say this is the primary and the secondary is also wound onto the same central limb. Like that. So, they are wound one about the other with an insulation layer in between. So, this would be the secondary. This is the E2, this is E1. Now, here of course, if I make it into an isometric 3D, this will look more like the transformer that we have here, and we have the terminals which are brought out here, and actually these points are soldered onto this. So, you could have these points which are soldered onto this, and the secondaries which are soldered onto this. And these are the laminations which you will see, the lines here, which are the thin laminations of the grain oriented silicon steel. Okay. Now, here you need to worry about few physical dimensions, which I will explain now. We will take that same core, we have the central limb, this is the 3-dimensional view of the core. So, we have the winding around the central leg. What is the maximum amount of windings that one can accommodate? So, if I cut, you will see that this is the number of windings that can be accommodated, both primary, secondary, all put together. So, what winding goes out will come out through this. So, it is the same loop. So, what goes out through here will come out. So, they have the current direction as coming out here and going in there. In this way. So, effectively we have this area only available to accommodate the windings. That is called the window area, AW. There is another important area that you need to bother about, and that is you have this of the central leg, or let me draw the other area which is also very important. And that is the core cross section area. Now, this core cross section area, let me show it in this different color. In this 3D image here, like that. Through which the flux are flowing, the perpendicular cross section area, that is the AC or the core cross section area. So, we have two areas here. One is called AC, which is the core cross section area. Another is called the AW, which is the window area. These are the physical dimensions of the core. How will you map these physical dimensions to the electrical property? One is by the Faraday's law. So, this is linked using E is equal to N d phi by dt, this is the Faraday's law, this we know, which is equal to N AC dB by dt. So, if you see that for a given number of turns and for a core with a particular swing in the flux density, E is proportional to AC. The core cross sectional area determines the voltage withstanding capability for the transformer. How much voltage it can withstand, beyond which the transformer saturates, because beyond which the volt second product will exceed the flux density capability of the core and the core will saturate. So, AC will tell you how much voltage a particular core can withstand. Then you have the AW. AW is related to the number of turns that can be accommodated in the window area, both primary, secondary put together. So, now that is going to depend on the thickness of the copper wire that you are going to use to do the winding, and the thickness of the copper wire is decided by what? It is decided by the currents flowing through the copper wire, because there is I square R loss and we can't have too much loss into the copper, and therefore, if we have I1 as the current flowing through the primary and I2 as the current flowing through the secondary, and let us say that J is the prescribed or the recommended current density that can be allowed in the copper. Normally, this is around 3 amps per mm square. This is a typical value. It can vary from design to design, power rating to power rating, but 3 amp per mm square is a typical value that one can expect in the copper wires of the transformer. So, what is current density? J, current density is I RMS by area of cross section of the wire. Area of cross section of the wire. So, area of cross section of the wire is dependent on I RMS by J, the recommended current density. So, you will obtain the A wire for the primary, the area of cross section of the wire for the secondary, based on I1 by J and I2 by J. Now, there are n one number of windings for the primary wire, n2 number of windings for the secondary wire. So, n1 into its cross section area plus n2 into the wire's cross section area of the secondary, all these must fit into the window area, into the available window area of the core. Now, A wire is dependent on the RMS value of the currents. So, the current carrying capability is decided by AW. The voltage capability is decided by AC or the cross sectional area of the core. Therefore, the product AC into AW should decide or should give an indication on the power handling capability of the core. This is the area product AP. This is called the area product, and this should decide the power handling capability of the core. Because this is deciding the voltage handling capability, this is deciding the current handling capability, and therefore, this decides the power handling capability of the core. This is the electrical parameter which is trying to map to the physical dimensional parameter of the core called the cross sectional area of the core. Another electrical parameter, the current, RMS current, which is trying to map to the window area of the core, another physical dimensional quantity of the core. AC, AW and sometimes AP are given in the data sheets of the core. V and I are calculated from the electrical circuit, and by this mapping one can choose what should be the size of the core for a given power handling capability, for a given power of the power that has to be passed from the primary to the secondary. The sizes of the core will be decided. Now, there is one more important deduction that we could do from the already known formula that we have, and that is E, which is equal to 4.44 N AC BM into F. This is the standard formula, that the voltage induced formula that we have derived for sinusoidal excitations for a transformer based on the Faraday law of electromagnetics. Now, here for our mains, which is 50 hertz, we are using normally the most common types of core materials in the market would be especially for the 50 hertz frequency is the CRGO, which is the cold rolled grain oriented, or the CRNGO, the cold rolled non grain oriented, which is slightly less expensive. So, if we are using, let us say CRGO, the cold rolled grain oriented, this would be around 1 Tesla as the design value. Let us say for 1 volt, for an AC of 1 meter square, we have 1 which is equal to 4.44 into 50 into 1 Tesla into 1 meter square into N. So, N is equal to 1 by 4.44 into 50, which is approximately 0.000 0.04 turn meter square per volt. This is for 1 volt, so many turns for 1 volt the area comes in, so that is the meter square per volt. This would be an approximate thumb rule which will give you at least a figure of what will be the order of magnitude of the turns that you would be applying. So, n is equal to 0.004 turns meter square per volt. So, let us say for E is equal to 230 volts and a core area which is 100 into 10 to the power of minus 6 meter square. This is the order of the magnitude of the cores, 100 to 1000 into 10 to the power of minus 6 meter square, which you will see the core cross section area. Let me take a value of 100 into 10 to the power of minus 6 meter square, easy for calculation, it is a small core. Then what is the turns that one would get, which would be 0.004 into 230 divided by 100 into 10 to the power of minus 6. This is approximately 10,000 turns. So, core of this size 100 into 10 to the power of minus 6 meter square core cross section area. If you want to apply 230 volts, you will have to approximately put around 10,000 turns to so that it can withstand that voltage and deliver the power from the primary to the secondary. Now, there is another important concept that one need to know about the transformer. The transformer, we said, has some applications. It can be used for isolation and it can be used for power transfer with step up or step down to make the voltages and the current compatible between one part of the electric circuit to the other part of the electric circuit. There is another important function that transformer can do, the impedance matching. Impedance matching. What I mean by this is, if you have a transformer and we have the source, the core like that, and let us say we have a impedance Z2 here. The turns ratio is 1:n. The voltage across this was E2, current through that was I2, current through this primary is I1 and the voltage here is E1 or EG. And of course, there is a dot polarity coming to the picture. Now, it is interesting to see what is the impedance seen by this source. What is the impedance seen by the source? So, the source impedance, so which means what is it equivalently the value of Z1 if we are to get the same I1 and E1. So, what is Z1 such that we get the same I1, and of course, the voltage across is E1. So, the source impedance Z1 is equal to E1 by I1. But this Z1 is supposed to be the reflected source impedance as seen from the primary, but the actual real impedance is on the secondary side, and that is Z2. And Z2 is E2 by I2. So, let us express E1 and I1 in terms of E2 and I2, that is the secondary side. So, we know that E1 is nothing but E2 by N, or E2 is N times E1, E1 is equal to E2 by N divided by I1 in terms of I2 would be N I2. So, which is 1 by N square E2 by I2, which is Z2 by N square. So, what it means is that if I have Z2 here, it is equivalent to having a Z1 which is equal to Z2 by N square at this point on the primary side. So, if I have a resistance of 10 ohms here and I have a turns ratio of N, then what appears here is 10 ohms divided by N square. So, if N is 2, it would be 10 by 4, which is 2.5 ohms on the primary side. So, it is a reflected resistance as seen by the source. A real 10 ohms load is seen as 10 ohms by N square by the source. So, actually the transformer is doing a transformation on the impedance value, and that is a very powerful feature, especially when you want to match the impedances of the primary side circuit and the secondary side circuit. Likewise, any impedance on the primary side to be reflected on the secondary side, it is the dual. So, if I have an impedance on the primary side, let us say I have Z1 a dot polarity. Okay. There is a current I1 and there is a current I2. This can equally be represented as an impedance on the secondary side which is Z1 into N square, where 1:N is the turns ratio of the transformer. Or if you have an impedance on the secondary side, can be reflected onto the primary side by dividing by N square. So, if I have a transformer with a core 1:N and let us say I have a a series resistance of 5 ohms, and this is 1:100, N is 100, and on the secondary side I have an inductance and a capacitance, inductive reactance of, let us say, 20 kilo ohms, capacitive reactance of 40 kilo ohms. Then I can equivalently represent it as looked from the primary side as a resistance 5 ohms, an inductance and a capacitance and a transformer which is like that. And so the amount reflected will be 20 kilo ohms divided by 100 square will be here, 40 kilo ohms by 100 square would be here. So which means this would be 2 ohms and this would be 4 ohms by n square. This is, and the current through this one, if this were I2, the current through this one would be also I2 by Ni2. The current through this would be Ni2, and the current here is equal to 0. Current here is equal to 0. This being an ideal transformer, So the transformer has very interesting properties of impedance matching. We will do few examples on these impedance matching issues in the next class, and then have a look at discuss the practical transformer in slightly more detail. Thank you.